I think I started talking about the definition of an interface in the last lecture. Um, so we will continue with that. The interface, even though they contain the smallest amount of the ingredient in a composite, especially in the case of ceramic matrix composites, they have an outsized influence on the final properties of the composite. And the interface is defined as the region between two discontinuous faces, for example, the matrix and the fiber. And it controls the properties such as the density, the elastic modulus, the strength, the thermal expansion coefficient, fracture toughness, etc. So you can calculate the interfacial area and based on the total volume of the fibers, total surface area of the fibers, and the cross-sectional area of the fibers. So from that you can calculate that. I'm sorry, I somehow it did not transfer exactly into this lecture, but if you look at the textbook, you can calculate the interfacial area. Okay, it will tell you that. And this interfacial area is also going to control the wettability of the fibers with respect to the matrix. And you can calculate that um, based on the wetting angle of the fibers. We will talk more about the interface in a couple of the future lectures, but right now this is sufficient for the time being. So the reason why we are interested in the wettability is that so that the matrix resin provides the best contact between the matrix and the fibers after the composite is formed. So I'm not going to go too much into depth about that. So you can calculate that based on the how what are the kind of angles, and there are specific equipments designed to calculate the wetting angle. Okay, so this is how the contact angle is defined, and it um, gives you the how well the matrix will spread over the fibers. So what do you know about the wetting angle and how it wets? So in order for good wetting, you need to have the matrix resin spread uniformly and in a thin layer across the fiber surface. So the perfect wetting is gotten when you have the wetting angle equal to 0, and if it is equal to 180 degrees, then there is absolutely no wetting. So which means that if the matrix resin tends to ball up over the fibers, that means that there is no wetting at all. And the reality is that the wetting angle is neither 0 nor 180 degrees. So there is a in between, and it is called partial wetting, and we get partial wetting in most of the resin systems. And it is also a function of contamination, temperature, roughness of the substrate, humidity, and the environment. If there is a lot of dust particles in there, then it is going to reduce the wetting. If there is humidity also, it can reduce the wetting. The environment can do that. And if there is roughness, then it can actually increase the wetting of the matrix resin on the fibers. And in order for the resin to spread uniformly and very nicely on the fibers, it has to result in a decrease in the total energy of the system. So S is for solid, L is for the liquid, and L is the liquid and V is the vapor. So the energy of the interface between the solid and liquid plus the liquid and vapor should be less than the vapor solid energy. We also want to see if we can get good mechanical bonding, mechanical interlocking between the matrix and the fibers. Because if you have mechanical bonding, it can improve the bonding strength and therefore the strength of the composite. And the other thing is that the thermal expansion coefficient between the matrix and the fibers also controls the final properties. For example, if you have a matrix that shrinks more than the fibers on cooling from a high temperature, it will result in a better gripping of the fiber by the matrix even in the absence of any chemical bonding. And if you have the matrix that is going to penetrate between any kind of ridges on the fibers, that also increases the bonding between the matrix and the fibers. In general, this mechanical bonding is a low energy bond with respect to the chemical bond. So the strength of the mechanical bond is lower than that of a chemical bond, but there are different cases that we might want to look at. So how do you improve the mechanical bonding between the matrix and the fibers? In order to do that, what you have to do is you have to roughen up the surface of the fibers. So how do you roughen up the surface of the fibers? You increase the area, the surface area of the fibers by, for example, by oxidation of the carbon fibers in the case of using nitric acid. And it can even be, it doesn't have to be very strong and concentrated acid, it can be a very dilute acid. So what it does is it creates oxygen bonds on the fibers, and those oxygen bonds can then bond with the counterpart atoms on the matrix resin when it is curing, and it forms good interlocking and mechanical bonding. In the case of fibers, we can also do what is called plasma treatment. So you attack the fiber surfaces with a plasma that creates some kind of ridges on the surface of the fibers, and those ridges can act as mechanical bonding between the matrix and the fibers. So both these increases the specific surface area, giving good wearing, and it also improves what is called the interlaminar shear stress of the composite. In the case of a metal matrix composites, you take, say for example, alumina fibers or glass fibers, and you attack that with metallic aluminum, and that also increases the strength of the bonds and therefore the mechanical strength of the bonding. In the case of ceramic matrix composite, you can do multiple things. We will talk about that in the future slides, but what it does is it enhances it controls the strength of the bond between the matrix and the fibers, and that provides better mechanical strength and better toughness for the composite itself. So for example, if you want good mechanical strength, you create what are called ridges on the fibers, and those ridges can act to hold the matrix resin atoms inside, and that reacts with the fiber surfaces. So it creates some kind of excess frictional bonding between the matrix and the fibers. So when you are trying to mechanically load the composite, those frictional bond has to be overcome in order for the composite to fracture and to break. So that gives you better mechanical properties and therefore a good thing to have. So you have what is called the rugosity or the surface roughness can contribute to bonding. only if the liquid matrix wets the reinforcement surface. If it is unable to penetrate the different regions of the fiber surface, then all you are going to have are interfacial voids. You don't want to have that kind of a situation. So this is regarding mechanical bonding itself. But what is more important are what are called chemical bonds between the matrix and the fibers. And these can be covalent, ionic, or metallic in nature. And the primary forces or the bond energy are between 40 to 400 kilojoules per mole. I mean, this is pretty high. I mean, these numbers may not make any sense to you, but that's pretty high. And when you have those kinds of bonds, short range interaction will predominate the bonding, the chemical bonding of between the matrix and the fibers. And the atomic species will dissolve into one another at the interface. And you also want to create the best bonds between the matrix and the fibers as possible. And so chemical bonding is the number one way to do that, and mechanical bonding is the number two way to do that. What is to be noted is that atomic or molecular transport by diffusional processes is what is involved in this type of bonding. There can also be compound formation on the interfacial zone, and there could also be solid solution. So you have a matrix resin, or you have different particles, and some atoms are displaced by the other atoms. That can also improve the chemical bonding between the different species, atomic species. So that's going to be controlled by diffusion theory. I'm not going to go too much into depth about that, but this is what is going to happen. So you want to improve the diffusion. So in order to do that, you have to heat up the material. So this is all. So this is a schematic of that. So you are going to be creating the interfacial region, and that interfacial region will control the bonds between the matrix and the fibers. So the whole thing is an interface. You have the matrix here and you have the fibers here. So you have different species changing in concentration from one end to the other. And you can control that by using the right kind of bonds and the right kind of surface treatments. So in order to measure this, you have what is called the short beam shear test, or it is called the interlaminar shear strength test, or ILSS. And it's basically you create what is called a V notch, and you apply some kind of a offset kind of a force on it. So the force required to break these bonds is going to tell you the interlaminar shear strength. And you want to have as good an interlaminar shear strength as possible. And these, the dimensions of this notch and the total dimensions of the composite, etc., have to be extremely precise, and they have to be according to ASTM standards. You also have other sorts of testing. One is called, you can pluck, it's like plucking the hair from your head. And people like me, we don't have much hair, so there is not much force required. But when you are a young person, it takes a lot of strength in order to pull that. So similar to that, if the strength is a very good one, that means it is difficult for you to pull the fibers out of the matrix. And it can provide very useful information about the interfacial strength in model composite systems. But it is not a very useful in the case of commercially available composites. And the reason is that you have to avoid any kind of fiber misalignment and introduction of bending moments in these composite systems. So again, so this is how the test is conducted. You have single fibers are fiber toes, you pull it out from the matrix, and the strength that is required, which should give you a reasonably good idea about the interfacial strength of the composite system. But this is not the best method for measuring the interlaminar shear strength of the composite systems. So what is the more important or more useful system? It is the fiber push-out system. In here, what you're doing is you're taking a nano indenter and you are pushing the fiber out. And what you do is you take a very thin sample, you polish that so that you can clearly see the fibers in the matrix, embedded in the matrix. And you apply a very small load and see how much stress is required, how much load strain, load stress, load displacement curve, what kind of load displacement curve you can get with respect to these composite systems. And it can give you the frictional shear stress acting at the fiber matrix interface. A valid push-out test will show a 3-region curve. And what it is, so this is a flat-tipped indenter, and this is a conical flat-tipped indenter, or it's a conical pointed indenter. These are the different kinds of indenters, but most of the time we try to use what is a conical pointed indenter to measure the interlaminar shear strength. So what you do is these are the individual fibers. You place your indenter on top of any of those fibers and see how much force is required in order to push it out of the matrix itself. So this is almost the end of the test. It takes it out and gives you the force that is required in order to do that. So this is the 3-phase, 3-part region for the push-out test. So you plot the stress versus displacement, and your test is only valid till here. This one is probably not valid anymore, so you don't want to, but you really cannot stop the test at exactly that point, so you let it continue, but you know that this region has to be avoided at all costs. You have to load several fibers in a polished cross-section of the composite system itself. So by doing that, you can measure the strength that is required in order to do that. So let me stop it here, and I will continue with the next set of slides.